So good afternoon everyone, I am Mateusz Groblewski and together with Wiktor Kania and Ewa Kłapcińska we want to present you FriML.
What is FriML, you may ask? It's a web app which, with only a few clicks to take your presentation into account, will generate a unique song. We have a website, the link is shown on the bottom left side of the screen. Feel free to check it out. As for the target audience, our product can be useful for game developers who either lack the funds to hire a professional composer or simply have no wish to outsource. Another group is content creators who wish to have a greater selection of royalty-free music so they don't have to worry about copyright. And moreover, AI-generated songs may be useful for musicians, whether as a base, inspiration, or if they find a beat that they particularly like.
We can divide our project into 4 parts: network, backend, frontend, and communication between them. Now let's look at all of them in detail. In our project we use RNN, Recurrent Neural Network. RNN is a loop of neural networks that are connected with each other with context. Generating song is like making a sentence. To make music that sounds convincing and natural, it needs to have a primer, which we can call the main topic of the entire composition. And this primer we must remember. In other words, we need to store a context. So let's go further. FriML is powered by the special kind of RNN called LSTM, long short-term memory, which is more than suitable for tasks like text classification, voice or image recognition, forecasting, as well as music generation. Our context here is remembered through cell state that gives information to next network. How LSTM works is simple and we can describe it in 4 steps. First, we forget unnecessary data. The value between 0 and 1 is calculated where 0 means forget and 1 is remember. Then it's time to decide what new data we want to keep. After that we just update our cell state. Thanks to this phase, the next iterations of this process will have the context we need. And the final phase is creating an output. And we repeat all these steps many times until we get awaited results. For example, if we get low loss value or after predetermined number of epochs.
But how does it all come together? The generation process starts with the client picking a genre. For each genre, we have one trained model and a dictionary file, which is used in translating the network output into nodes. We generate the network input using those nodes from the dictionary and feed them into the model. Then we use the output and, again, using the dictionary, translate it into nodes. We save those as both a JSON file, which is used to play the song on the website, and as a MIDI file, which is available for the customer to download.
To train our models, we've been using a few datasets. The most important one is LAC-MIDI dataset, including about 45,000 songs. It consists of many genres. We especially used 3 of them: rock, pop, and classical. We also said before that one of our targets is game development industry, and that's why we also included NES MDB that allows us to generate video game music. The dataset was created with researching how NES music and NES synthesizer worked and machine learning in mind, so it was the most suitable one for us.
Okay, so let's delve into the architecture of FriML. It is divided into 3 separate components. The first one is a static website. This is what the user sees. It has web files such as HTML, CSS, and JavaScript, and it connects to the Node.js server. The Node.js server acts as a proxy between users and the Python server. The Python server is responsible for generating songs. The reason why we need this kind of architecture is because, song generation is a pretty heavy process, and most machines are not able to run more than one at a time. Plus, most hosting providers will definitely not run more processes at a time. At the same time, though, we want to allow multiple users to interact with our app. That's where the Node.js server comes in. By using lightweight WebSocket connections, it proxies data sent by users to the Python server, but it queues requests. So the Python server does not get overloaded. The generated songs are then sent back to the user through the Node.js server. Let's take a look at the user interface. The first screen is the genre selection screen. We have 4 of them to choose from, and this choice later affects which model will be used to generate the song. Next, there's the key selection screen. This choice affects which key the generated song will be later transposed to. Then there's the instrument selection. This will only affect the sound of the output. And at the end, we've got the results screen. You can play the generated song in the browser or download it in MIDI file, format file, to, for example, edit it later or maybe add some of your stuff. If you choose to play the song in the browser, it will be presented with a simple visualization showing every note in real time. Additionally, our app is not a closed system, nor is strictly connected to our web app. It is built in a way that allows to connect other software to it. For example, we managed to create a chat app plugin that allows to control Frame by sending text commands. Some of you may know this software. It's Discord, pretty popular among teens and young adults today.
Okay, so now we have prepared a little mock-up showing an example game with all music generated by our project. Let's take a look. And that's the end. I hope you could hear a music because, well, that was a main point of this mock-up video. And that's all we have to show you. Feel free to ask some questions, and thank you everyone for your attention.
There is quite some info we couldn't manage to fit into presentation, so please do ask us questions if you have any.
Good, thank you. So please, we open the floor for questions.
I have a short question. First of all, I would like to congratulate this really interesting project, fantastic project. And the question is it any chance to extend this kind of application to normal music, not MIDI?
Well, we can. Well, it is generated in MIDI format because that's what people use in, for example, digital audio workstations for composing music and editing it. So it's really simple to, for example, then just import it into DAW and use some favorite VSTs for electric guitars, pianos, strings, etc., and make it more realistic and not MIDI sounding. To be honest, many MIDI sound fonts really sound great. It's just that to fit it into the game style we shown that represents more 16-bit Super Nintendo games. That's why we've been using SNES more sounding SNES type music here. That sounds like games from the 90s.
We also, in the aerial version of our app, generated a WAV file alongside the MIDI file, but that process was too demanding it was okay on a local machine, but we want to make this a web app that is available to everyone. So we had to cut it down, unfortunately. But yeah, it was possible to also generate a WAV file that is not a MIDI file.
Yes. So if you would use a paid hosting service to something like that we could just import sound fonts and generate WAV files with that.
Thank you very much. Just comment. It's of course it's complete project with focused application, and congratulations, good work. Thank you.
Thank you very much.